So, welcome to the afternoon session. It is Mario from Madrid who will talk about the title which is written here. Please.
Thank you, Thomas. Okay. Thank you so much to the organizers for the invitation. It's so nice to be here. It has been a while since this conference was organized, and finally we can meet in person. I'm very happy to be here in Toronto for this. I'm going to present some work which is joint work with Luis Alvarez Consul from the ICMAT in Madrid, and our joint PhD student Andoni de Arriba de la Era, who is here in the audience. So Andoni is there. Andoni is about to finish his PhD this year, and if you want someone who has very strong vertex algebra calculations, you should hire him. He will be in the market very soon. So what I would like to talk about is some form of mirror symmetry which happens in non-Keller manifolds. And let me start by some motivation. So as you know, Witten defined in 1982 two truncations of the superconformal field theory that you can associate to a Calabi-Yau. These are called the A model and the B model. The A model has to do with the symplectic geometry of the Calabi-Yau, and the B model with the complex geometry. So the basic principle is that these two theories, the A model and the B model, are exchanged, and therefore for mirror manifolds, for mirror Calabi-Yaus, we have an exchange of the complex geometry in one of them with the symplectic geometry in the other. In particular, modular spaces for the formation of complex structure on X are exchanged with the so-called Keller moduli on the mirror. Okay, and this is the typical picture that physicists write down, where they plot the Hodge numbers of Calabi-Yaus, suitable combination of them, and then you realize mirror symmetry. An effect of mirror symmetry, that's this picture for all the known SU of Calabi-Yau manifolds has this symmetry through the vertical axis. Okay. In 1984, yes, 2 years after in this A model and B model were introduced by Witten, Morrison, Aspinwall, and Green realized that one complex Calabi-Yau, one Calabi-Yau manifold, its complex structure moduli space can have multiple mirrors. What does this mean? It means that there are some Calabi-Yau manifolds which have a very big complex structure moduli space, and in order to realize a Keller moduli space which is mirror to that, you need to ensemble several Keller moduli by their boundary, and this is this picture of this cone, or the complexified Keller cones of several Calabi-Yaus, which are related by a suitable surgery operation, which is called a flop. What is a flop? So essentially, you start with some. This is an example, but you start with some Calabi-Yau, which has some embedded rational curves, whose normal bundle is O-1 plus O-1. Then you can construct them and get to some singular Calabi-Yau threefold. If you blow up that, you get to some Calabi-Yau which has accretional divisor P1 cross P1, and then you have two possibilities for constructing one of the two P1s. One of the two P1s, constructing one of the two P1s recovers the original Calabi-Yau, and constructing the other and gets to some other Calabi-Yau threefold, which is related via a rational transformation. It may happen that X prime, if X naught is not algebraic, it may happen that X prime is also non-algebraic, not even Keller. And this typically occurs when you have complex manifolds which have very small second homology, and then by constructing rational curves, which are spheres, you can kill the full second homology and end up with something which is non-algebraic here. Okay? This is an algebraic example, but this may happen. So then, via this observation of Aspinwall, Green, and Morrison, there is the question of what happens with mirror symmetry when you end up in a non-Keller manifold. And of course, the main caveat here is that in a non-Keller manifold, you have no symplectic geometry at all. Okay, so what happens with the A model? Another possibility for constructing non-Keller, non-algebraic manifolds from algebraic Calabi-Yau is doing a conifold transition. So essentially, we have the same picture as before, but our singular Calabi-Yau, which is obtained by constructing suitable rational curves, is you do to it a smoothing. So you deform the comp structure to something else. And this, by doing enough contractions of rational curves and enough smoothings, you may end up in something which is very, very, very non-algebraic, non-Keller. And these manifolds, which are obtained via transitions and flops, after doing enough of these conical transitions, you may end up with something which is of this form. These are copies of S3 cross S3, which you glue. This is like a three-dimensional model or a three-dimensional analog of a Riemann surface, okay, in complex one dimension. And this, as I was mentioning before, these surgeries, these conical transitions and flops, have an effect on the topology. Conical transitions have even a more drastic effect because morally you exchange second cohomology with the third cohomology of the manifold. Okay, so in the end, by doing enough of these surgeries, you may end up in something which is non-Keller, and then you wonder what happens with mirror symmetry for those. So in particular, there are examples of rigid Calabi-Yau threefolds for which you have no deformation of complex structure. If we believe the physics picture for mirror symmetry, they should have a mirror, and the expectation is that a rigid Calabi-Yau threefold, meaning rigid as for the complex structure moduli space, should have a mirror which is one of these Clemens-Friedman manifolds, which are taking copies of S3 cross S3 and gluing. Okay. So this picture has motivated a lot of work in mathematics in recent years about how to extend mirror symmetry to non-Keller spaces, to non-Keller complex manifolds. And there is work by Lau, Zheng, and Yao in the SYZ approach, also by Aldi Helwani using Vertex Algebras, also more theoretical point of view by Popovicki, and more recently work by Agu and Ward on the homological approach by Koncevic. So all these approaches share common features with the algebraic case in the following sense. They are constructed, or they are based on two-dimensional conformal field theories, which have a lot of supersymmetry, 2, 2 supersymmetry. Okay, and in particular, there is some sort of replacement for the A model and the B model, and these are exchanged. Okay, and what I'm going to talk about in this lecture is another form of mirror symmetry, which is based in sigma models with less amount of supersymmetry. Okay, so in this talk, I wanted to explain one example of something which in physics is called 0-2 mirror symmetry. Okay, so it's a toy model for mirror symmetry based on sigma models which have only half of the supersymmetry, which typically occurs in mirror symmetry. So for this is this preprint with Andoni and Luis. For this, I'm going to build on an approach to mirror symmetry introduced by Borisov using Vertex Algebras. I will try to explain what this is. And yeah, the idea is that this is only one example, but it seems to provide a path to address this generalization of mirror symmetry called 0-2 mirror symmetry for sigma models with a low supersymmetry, or less supersymmetry than 2, 2. Okay, so in 0-2 mirror symmetry, what is the analog of the A and B models? Okay, so as I told you at the beginning, we can define these A and B models, which are truncations of the superconformal field theory associated to a Calabi-Yau. In the same paper, we can also define something called the half-twisted model. It's another simplification, another truncation of the superconformal field theory. And then what he claims in the paper is that mirror symmetry should exchange A and B models, and it should map a half-twisted model to another half-twisted model in the mirror. Okay, and this is the replacement for the exchange of A and B models in this other form of mirror symmetry. So where can we expect these 0-2 mirrors to occur? Well, the expectation is that if you have a non-Keller Calabi-Yau threefold, I mean, you have a Calabi-Yau threefold which possibly is non-Keller and which is equipped with a holomorphic vector bundle over it, satisfying suitable constraints on the chain classes. In particular, this is very important. The second chain class of the bundle should be the second chain class of the manifold. Or more generally, if this is not the case, if the first chain class is non-zero, then the second chain characters should agree. Then out of this data, you should be able to produce a half-twisted model. And for mirror pairs, meaning for pairs Calabi-Yau and bundle, this should have a mirror, and the half-twisted model should be isomorphic, whatever this is. Okay, so how to construct mathematically, or how to make sense mathematically of what it means this half-twisted model? And this is via the theory of vertex algebras. Okay, so let me give you a very short introduction to what a vertex algebra is, and then I will explain you some constructions by Malikov, Sheshman, Weintraub, and also Helwani and Sabsin, which give you a tool on how to construct this half-twisted model mathematically. So a vertex algebra is a notion, an algebraic notion, which was introduced by Borchers to produce or to prove the Moser motion conjecture. And the basic gadget is a vector space V and a state field correspondence. So V is supposed to be the space of states of some physical theory, and then you have some machine Y which sends any state to some operator, and this operator is kind of funny because it is a distributional valid. It's a distributional valid operator, and these are what this bilateral series tell you about. Okay, so the idea is that you should think of this vertex algebra as an algebra of operators on a Riemann surface, but these operators have some distributional character or a distributional nature, so that when two of them collide, they produce singularities. Okay, and this is what is keep tracking this operator product expansion for the fields. So the most basic identity that is
Is this equation asymptotic only, the last one?
this is a formal power series, so there is no limits or anything. Is this what you mean? Or
usually it's Z, you're very close.
Yeah. The idea is that this is getting close to this, and then you produce a singularity, and this is the new field which is previous. Yeah.
It's supposed to be the whole thing because you're far away. If Z and W are far away, that's the same thing. Or
I mean, this is supposed to model like when the two operators interact. Okay. Yeah. Oops, sorry. So the most basic identity is Borcher's identity, which tells you what happens when you take. So these circles are supposed to represent integral contours, and contour integrals. So when what this picture represents is what happens when you, on the one hand, first interact with this field in this field and then act on this state, or you act on this state by this field and then by this field, or you act on this state by this field and then by this field. Okay, there is a relationship which tells you how these things commute when you do this sort of colliding of the fields. Okay, so how do we relate this very complicated algebraic structure with this half-twisted model that I was telling you about? So the idea is the following. So by work by Malikov, Sheshman, Weintraub, and Korjunov, and also by Bressler, whenever you have a closed tree form on a manifold, then you can associate a sheaf of vertex algebras. This is an oversimplification. I'm not telling you many details here because the complex tree form has to satisfy suitable properties. But in general, this is the idea. Okay, so whenever I give you a closed free form on a manifold, I'm going to associate this sheaf of vertex algebras. And then for a Calabi-Yau manifold and h equals to 0, Kapustin proved that the cohomology of this sheaf comes with a natural differential, and you can take cohomologies. The cohomology of the sheaf is related to infinite volume of the half system model. Okay, so the half system model is a truncation of the superconformal theory associated to a Calabi-Yau, but it has a very subtle dependence on the metric. And when you take this metric to be very, 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 very large, this physical half system model is recovered by the cohomology of this sheaf of vertex algebras. Okay, that's the idea. And now, once you have this sheaf of vertex algebras, then you can try to define mathematically the half system model by constructing embeddings of a suitable particular vertex algebra, the n equals to 2 superconformal structure, into the global sections of the sheaf. And this is work by Helwani Sapsin based on some general construction in the physics literature. What they are able to show is that under some geometric conditions in the manifold, you can construct a specific embedding of a suitable vertex algebra, which is this n equals 2, with these relations for the Fourier modes of the fields. So L, J, G plus, G minus are vectors, and then via the state field correspondence, you promote this to a field, and these are the relationships satisfied by the Fourier modes. And once you have this n equals to 2 structure, there is a natural procedure that you can do to construct the half system model by taking suitable cohomology. And the comment I would like to make here is that
sorry, how is the half system model defined now? By some vertex algebra.
You construct, so you have your sheaf of vertex algebras, you geometrically construct an embedding of the n equals to 2, and then using Fourier modes of some of the fields of the n equals to 2, you take a suitable cohomology. So this, I think it's with L and J, you construct a suitable differential operator, and then take cohomology for that, and that's the way you have defined the half system model. That's the idea. Okay, I will be more concrete in.
What is the VH?
Sorry?
What is the VH?
VH is the sheaf of vertex algebras that you associate to your closed free form. Say, okay, I will be more specific later. Okay, so we know how to do this in some examples by the work of Helwani and Sapsin, but unfortunately, all the cases for which we know how to construct this n equals to 2, which are some structure called generalized Calabi-Yau metric. There are some no-go theorems which tell us that the only Calabi-Yau metric structures on compact manifolds are just Calabi-Yau in the Keller case in the usual sense. Okay. So if we want to use this picture for extending mirror symmetry to non-Keller manifolds, we need some more flexible structure. And then once you have this n equals to structures associated to a suitable geometric structure in your manifold, you can define mirror symmetry following Borisov by saying that you have an automorphism of an isomorphism of the cohomologies of the vertex of the sheaf of vertex algebras, which realize the mirror involution, which is this shift on the fields. Okay, so L, J, G plus, G minus goes to L hat minus G hat, G hat minus G hat plus. Okay. So the full question about defining or finding examples realizing mirror symmetry in non-Keller manifolds here reduces to how to construct embeddings of this n equals to 2 structure on the sheaf of vertex algebras associated to some closed free form, say, or more generally a current algebroid, and then how to make this isomorphism concrete, and how to realize the mirror involution. And this is what I would like to take you next.
Which generates are even and which are odd? Which generates? So G's are odd.
L and J are
even.
L and J are even, and the G plus and G minus are odd.
Yeah. Okay.
Yeah. So L is Virasoro, J is the current, and then J placing dimensions are the two further generators of the n equals to 2. So L and J together gives you the n equals to 1. Okay, so before going into brackets, which I know this is the main thing of this conference, I would like to tell you a little bit about what is the geometry that we use in order to construct this n equals to 2. Okay, so I'm going to fix a compact complex manifold of dimension n with vanishing first-term class in integral cohomology. And then I'm going to consider SUN structures on them, okay? This is going to be a generalization of the condition of Calabi-Yau for a metric. An SUN structure is a pair Fc omega such that Fc is a complex N0 form, like a holomorphic volume form, but this is not going to be holomorphic, it's only smooth. And omega is a 1-1 positive form. So rotating by J, the omega gives me a metric, which is Hermitian. And then the SUN condition is that the norm of Fc with respect to the metric is 1. Okay, it's normalized. So out of this, there are two quantities that I can associate. In Hermitian geometry, one is the Lie form, which is very important. You take the adjoint of the zero differential of omega, and then you rotate by J. And the other one is a special connection, which plays the role of the Levi-Civita connection in this context, which is called the bismuth connection. So you take Levi-Civita, which is nabla G, and then add torsion, which is precisely given by, after raising one index, is given by dc of omega. And then I'm going to consider this geometry, this twisted Calabi-Yau equation, which I introduced in joint work with my collaborator Rubio, Sebastian Tipler, which has these three equations in it. Okay, so let me comment briefly. So this tells me that psi is not closed. If it were closed, it would be a holomorphic because it's n0, but it is locally closed because theta omega is closed. So it means I can choose a local potential. Okay, so in particular, the complex structure is going to be, well, I'm assuming this from the beginning, but say that psi is up to rescaling by a local function, which is prescribed by the Lie form, is a holomorphic volume form. Okay, it's conformally a holomorphic volume form. And then I impose this condition on omega, which is a relaxation of the condition of being Keller. Okay, it's called the pluriclosed condition. Sorry? DC is this operator. So DC is I d bar minus I del. Okay. So what you are ddc of omega equals to 0 is 2I del bar omega equals to 0. Okay. So instead of imposing that d omega is d closed, I impose that it is dd bar closed. Okay. So why to consider this geometry? So the first observation is that solutions of these equations gives you steady solitons for the one loop renormalization group flow, okay, of a two-dimensional sigma model. This is not obvious, but it's true. It's based on some joint work with Jeff Streets, and one can prove that if you have a solution to these equations here, then there exists a suitable function which plays the role of the dilaton in your sigma model, for which you have a stationary solution of these two equations here. So you will have and this will be equal to 0, and this will be equal to 0. And here H is precisely the torsion, it's minus the torsion of your bismuth connection. This is good because we are trying to construct suitable n equals to 2 subconformal structures, and the renormalization group flow is supposed to flow to a superconformal point. So this makes sense at least. Yeah.
I was a bit lost. So why do you have this renormalization group flow equations again?
What I'm saying is that if I have a solution to this, to this 1, 2, and 3, then I get a solution of the renormalization group flow, which is stationary. It means that with T so the metric and the 3 form do not vary. Okay, so I will have this equals to 0 and this equals to 0. G will be the metric in the solution, and H will be the torsion. Yeah, that's my point. That since we expect that the renormalization group flows to a superconformal point. At least it makes sense because we are having some steady solidity for this flow. Okay. So another reason why this geometry makes sense is because it recovers Calabi-Yau simply by imposing that the first chain class, by the cohomology class of the leaf form is 0 in cohomology. In particular, if you have a simply connected manifold, then any solution of this is going to be Calabi-Yau in the usual sense. Okay, a Calabi-Yau metric which is scalar. Okay, and this is another comment that there is a way of relating this to this bigger picture where you have also holomorphic bundles in place.
What is capital?
Capital omega is the holomorphic. This will be the holomorphic volume form on your Calabi-Yau. And is in this case, so in that case we don't have a holomorphic volume form, but imposing that the class of the leaf form is 0, say that you have a global potential for the leaf form, and therefore the psi can be globally rescaled to a holomorphic volume form. And this is the one which appears here. Okay. So more generally, if instead of imposing DDC of omega equals to 0, I take some sort of source, then the expectation is that what I'm going to tell you later is going to also generalize to that case. So this rho may represent two things. On the one hand, some sort of gauge theory, which is related to some equations which appear in heterotic string theory called the Halle-Strominger system, or some bunch of branes in your Calabi-Yau. Okay, and this is actually going to be the relevant case for us. Okay, so what do we know about these equations? Do we have any non-Keller solutions? Because I'm trying to construct this mirror symmetry in non-Keller manifolds. So we have this classification result with Rubio, Savasi, and Tipler, which tell us the following. So assume that you have a compact complex surface. So in the case of n equals 2, complex 2 dimensions, with vanishing first in class, then X admits a solution if and only if one of the following holds. In the case that the class of the leaf form is 0, this first case, then the only thing you have is either K3 or T4. So we are back in the useful Calabi-Yau case for complex surfaces. But there is one more possible solution, which is that if the class of the leaf form is non-zero, then I can have a Hopf surface. Okay, a Hopf surface is a quotient of C2 minus the origin mod by a radial set action. So if you think of C2 minus the origin as S3 cross R, then what we are doing is to compactify this R direction. Okay, and then we get S3 cross S1. Okay, and there is some suitable cohomology class, which is a generalization of the Keller class called the Apley class, which codifies the possible solutions of the equations in this case. Okay, this is what I was saying, that in the case of a Hopf surface, we have S3 cross S1, and we have no second cohomology, so this is a non-Keller manifold, a complex non-Keller manifold, and there is a suitable replacement of the Keller cone by using this Apley cohomology, which is somehow natural in complex non-Keller geometry. Okay, I don't want to go any further into that. I just wanted to give you this glimpse on that we have some geometry, which I propose as the right geometry for constructing these n equals to 2 structures in non-Keller manifolds. So let me give you one example in the Hopf surface just to show you that this is very explicit. I'm not going to show you this. I'm going to show you this. Yeah. So out of a parameter x, which is a real number, I can construct a particular Hopf surface, which is the quotient of C2 minus the origin by the radial set action generated by e to the x in each coordinate. Okay. So yeah, I act on the two coordinates in C2 by multiplying by e to the x, and x is some real number. Then in upper stairs, in the universal cover, so in C2 minus the origin, I can write these two explicit formula for the Hermitian form and the 2-0 form. This is totally explicit, right? Essentially, this is the flat metric divided by norm of Z squared. And similarly for the 2-0 form. And I claim that this gives you a solution, and actually the parameter L is precisely the cohomology class of the torsion of this C of omega, and the parameter L times X is essentially this Apley class. there is a physical interpretation of this solution, which is back to work of Callan, Harvey, and Strominger in this paper about supersymmetric string solitons. So the way to think of this as some sort of a physical solution of heterotic string theory is to go to the universal cover, to go to C2 minus the origin, and then when you do DDC of omega x, what you get is L times the Laplacian acting on normal set to the -2, and this is L times the delta function located at the origin. So what this is telling me physically is that I have one of these sources on the right-hand side of my DDC omega equation, and this is precisely given by L branes located at the origin. Okay, and there is some relation with black holes, which is not relevant for what I'm saying. Okay, so now let's go for the brackets now. I told you what is the right geometry, or a proposal for the right geometry, and now I want some way of, out of this geometry, produce these n equals to 2 structures. So for this, I need the following definition. So let G be a quadratic Lie algebra. Okay, so I have a Lie algebra with an invariant pairing. I'm going to assume that the pairing is non-degenerate. Then I say that I have a solution of the Killing-Spinor equations on this quadratic Lie algebra if I have a triple B plus epsilon and eta, where B plus is a generalized metric. It means that it is a decomposition of G into some subspace and its complement, its orthogonal complement, and the ambient metric restricted to B plus is going to be positive definite. Epsilon, which is simply an element in B plus, is a geometric or an algebraic version of what we call a divergence on a Courant algebra. A divergence, as in the paper by Pingshu and Anton Alexeyev. I can explain this later, why this is a divergence. And then this eta is going to be a spinor for B plus. Okay, so I take an irreducible representation of the Clifford algebra for B plus, and I take a non-zero element in here, which I'm going to further assume later that is a pure spinor, but this doesn't matter. And then I just impose these two conditions. Pi? Yeah. This pi minus? Yeah. Yeah. Pi minus is the projection. So you have this decomposition of G. Okay. Pi plus is the projection in here, and pi minus is the projection in there. Okay. So this equation here, morally, yeah, the A's are a basis for B plus, okay, which is orthonormal, and the A super J's are the dual bases with respect to the, I mean, in this case, because I'm assuming that this is a signature, Euclidean signature, the I super J's are just the A super A's. So there's nothing. So you can think of this as an orthonormal basis. Okay. So the first equation here essentially tells me that there is a suitable connection which is annihilating the spinor. Okay. And the second equation tells me that there is a suitable Dirac operator which is annihilating the spinor. It's not, sorry, it's not annihilating the spinor. It's proportion such that, I'm sorry, this Dirac operator acting on the spinor is this epsilon element times the spinor. Okay. So this looks like taken from the hat, but this is an axiomatization, say, or an abstraction of the Killing-Spinor equations which appear in supergravity in physics, formulated in a Courant algebroid first, and then taking the Courant algebroid over a point. And this is the result I wanted to mention on how to go from the geometry to the algebra. So suppose that you have an even dimensional compact group, and the example you should be thinking of is precisely the example I'm going to focus is SU2 plus U1, which is precisely the geometry of the Hopf surface. So suppose that you have an even dimensional compact group, and suppose that you have a left invariant solution of this twisted Calabi-Yau equation that I was telling you before. Then you can construct a natural quadratic Lie algebra out of this data, which is the following. You take tangent plus cotangent on the Lie group, and then you take the Dorfman bracket associated to the free-form dc of omega. So dc of omega is closed. I define H to be minus dc of omega, then d of H is 0. And then there is a natural Dorfman bracket on sections of tangent plus cotangent. Let me not write it down unless you ask. This bracket has some kind of weird properties. It satisfies the Jacobi identity, but it is not symmetric. Nonetheless, if I take invariant sections of tangent plus cotangent, then this gives me actually asymmetric, an antisymmetric bracket. Okay, and this recovers a quadratic Lie algebra. Okay, so what I'm going to do is to take invariant sections on tangent plus cotangent with respect to this twisted bracket. And then the claim is that this left invariant solution of the twisted Calabi-Yau equation gives me a solution of the Killing-Spinner equations in the algebraic sense, as in the previous slide, on this object here. Okay. Okay, I was saying that I'm not going to show you, but it's actually written in the slides. So I forgot what I wrote in the slide. So the point is as follows. So you take that d of H is 0, where H is minus dc of omega, then you have a Courant algebroid, okay? In this manifold, which is M is equals to K. It has this bracket, sorry, this pairing, just given by pairing one forms with vector fields, and this bracket. This bracket satisfies Jacobi, but it's not skew symmetric. But the difference, or the way it differs from being skew symmetric, is d of a function. So if we take invariant sections, then this vanishes, and then on left invariant sections for tangent plus cotangent, we recover a quadratic Lie algebra. Okay. And yeah, as I said, the proof follows from some abstract characterization of this twisted Calabi-Yau equation using very general Courant algebroids existing containing this in this paper here. Good. So now we have this catalyzer which takes us from the geometry to the algebra. And now I can start talking about these vertex algebras and killing spinners. So now what I'm going to do is to do the following. I'm going to take a quadratic Lie algebra, associate a vertex algebra to it. In this quadratic Lie algebra, I'm going to take a solution of the Killing-Spinner equations and then use that to embed n equals to 2 superconformal structures into the super definition of the quadratic Lie algebra. But for this, I need some machinery. So I'm going to stick to this definition or to this approach to vertex algebra, which is due to Helwani and Kak, which uses the superfield formalism. So I start with the translation algebra, which is an associative superalgebra over C generated by an odd generator S and an even operator T, says that S squared equals to T. And then I have this definition of SUSY Lie conformal algebra. I will explain what this means conceptually in 2 slides from now. Then a SUSY Lie conformal algebra, following Helwani and Kak, is a P model R. Sorry?
S and T are operators where? Or
yeah, S and T are operators on R. Okay, so I have 2 operators, one odd, one even, S squared equals to T, and then these are going to act on R. Okay. Is this the translation algebra is generated by 2 elements over C with this relation?
Ah, okay.
Yeah, this is the definition, of course.
Why would you say generated by S since S squared is T, so T is not a generator then?
What I mean is that I have a C vector space.
Oh, in that sense.
Okay. No. It's the C algebra in S and T, and then I impose this relation S squared. Yeah, I don't know. Maybe it's you don't need to present it that way. I don't know if there is. Yeah. Anyway. Okay, so associated conformal algebra is given by a pin module R, a lambda bracket, which takes two elements in R and sends them to R tensor L, where L is, this is essentially another copy of the translation algebra with different generators, but these are polynomials in variables he, which is odd, and lambda, which is even, subject to this relation here. And you have suitable actions, which tell you how the operator S gets out of the bracket, what is in the two possible entries, what is the failure of this to be a skew symmetry, and also what is the failure of this to satisfy the Jacobi identity.
What is B minus, for example?
Sorry?
What is, for example, B minus? Or what is, I mean, the failure, this second to last equation.
Oh yeah. So what you say is that if you take this formula, which is going to be a polynomial in variables he and lambda, what you need to.
So A and B live in L.
Sorry?
A and B live in this curly L.
A and B live in R.
No.
Okay. I take the lambda bracket of A and B, and to relate it to this other thing, to the bracket of B and A, what I need to do is to take the bracket of B and A in some other formal variable. I get a polynomial, and then I replace the variables in my polynomial by minus lambda minus delta.
But what is lambda? Sorry,
So
you didn't say what lambda is.
yeah, the lambda is a parameter. Yeah, it's yes the. No, this is so A lambda B is a bracket which takes values in this polynomials tensor R, right? So now I apply this, I get a polynomial, and then I take the lambda bracket of B and A, and whatever expression I get in a formal variable, I replace it by minus the variable he minus the variable lambda, and then delta is you have to think of it as a pair ST. Okay, so whenever I get the new variables he and lambda, I'm going to replace this in this expression by minus he minus lambda and also minus S minus T, acting as operators on whatever I get on the right. Did I make my point or not?
This nabla is a kind of derivative?
The nabla is some notation for the pair ST. Okay. So you get a polynomial in he and lambda, and then you replace formally this by minus he minus lambda and also minus S minus T, acting on whatever you have on R. Okay.
Okay.
And similarly, this is another mess, but it follows the same principle. Okay. So let me give you one example which is relevant for what I'm going to tell you next. So this is the n equals to 2 algebra. So you take R to be the translation algebra tensor CH plus CJ plus C. These are some formal variables, H and J. The H is going to be odd, and the J is going to be even. Sorry, the other way around. J is odd, H is even. And then I have brackets which are given by this formula. Okay, H with H is H plus some central element C, which I'm going to call the central charge. Actually, this is a constant, and then J lambda J is this other thing, and there is also this third bracket.
And lambda and chi are this, some kind of parameters in this strange ring globe.
Yeah, the lambda and chi is another presentation of the translation algebra, but these are just formal parameters. Okay. Yeah. Oops, I should go in the other direction. This is more geometry. So take a Lie algebra and do it with an invariant pairing. So take a quadratic Lie algebra. Then I have the algebra of currents, of supercurrents, which is P tensor G change parity plus some C, some copy of C, which is going to be central. And then the lambda brackets for elements in G change parity are going to be given by this expression. So A change parity lambda bracket with B change parity is you change parity to the bracket of A and B plus 2 he A times B using the pairing. There is a beautiful explanation for what this means, which is actually thanks to Thomas and Anton in a paper in the non-supersymmetric version, which has to do with thinking of elements in curve G as left invariant sections of tangent plus cotangent on a compact Lie group, regarded as distribution of valued smooth functions in the loop space. So morally, what happens is that if I take, for example, a one form in my compact Lie group, then I can regard it as a function in the loop space of the cotangent bundle by integration. So you take an element in the loop space of the cotangent bundle, you it's better to do it with vector fields. So you take a vector field, you take an element in the loop space of the cotangent bundle. So you pair the vector field with the cotangent direction. This gives you a function, and then you integrate with respect to some measure that you fix on S1, to some volume element in the S1. And because this is an integration, you can insert functions, which you smooth functions on the circle, which you realize as a test function. So this has some distributional nature. So the way of thinking of the lambda bracket is as a distributional enhancement of the Poisson bracket on the loop space of the cotangent, and then quantizing this the natural commutative product in functions yields the notion of SUSY vertex algebra, which is what I'm going to tell you next. So following Helwani and Cox, a SUSY vertex algebra is given by a SUSY conformal algebra as before, a specific element in B, which is a non-vanishing element, which we call the vacuum, and a normally ordered product, which is like the quantization of the commutative product in the loop space of the cotangent. Okay, and these are subject to suitable complicated actions, which are even more complicated to explain than the previous identity that I was struggling to explain before. Okay. There are two important results about this. One is the reconstruction theorem, which tells you that essentially, if you give me a SUSY conformal algebra, in particular, if you give me a quadratic Lie algebra, I can associate the algebra supercurrents. And this SUSY conformal algebra can be quantized in a canonical way to a vertex algebra, okay, to a SUSY vertex algebra. And the other thing is something I told you at the beginning when I introduced this, that there is a state field correspondence. So here I'm using this superfield formalism. So in addition to the variable set, which is like a variable in my Riemann surface, I have also some odd parameter theta, which is going to keep track of the odd directions. So let me give you this final slide of this part just to reconcile what I have told you in this Helwani-Cox formalism with superfields with the thing I was telling you before about vertex algebras. So suppose that we have the n equals to 2 SUSY vertex algebra associated to the SUSY conformal algebra that I was mentioning before. Yes, P tensor CH plus CJ plus some abelian factor. Then via the state field correspondence, I have these fields. So this should be curly J and this should be curly H. So my curly J goes to this particular field, and my curly H goes to these particular fields. And then the relations of the n equals to 2 in the classical sense are recovered from this more complicated, or this not more complicated, the other way around is this condensed way of writing the lambda brackets. Okay, so these relations here give you precisely the relations of the n equals to 2 in terms of the Fourier modes. This thing here, okay, which is what typically you find in the literature about conformality theorem. My time is over? No, I have like 5 more minutes, or? Okay. Where I'm going now, where is this? Okay, so this is what I want to present now. The main results are how to embed n equals to 2 or how to construct the embeddings of n equals to 2 into the vertex algebra of supercurrents using these Killing spinor equations. So given a quadratic Lie algebra, I consider the vertex algebra of supercurrents. How would we construct embeddings of n equals to 2? So I go back to my definition of the Killing spinor equations in a quadratic Lie algebra, given by this orthogonal decomposition and a specific element in V plus, and this non-vanishing spinor. So recall this is like the spinor being parallel, and this is like the Dirac operator on the spinor being proportional to epsilon acting on the spinor. And what is going to be relevant for my situation is the case of even dimensions. So assume that the dimension of V plus is even, and that eta is pure. Then a solution of the Killing spinor equations in this situation is equivalent to the composition of B plus tensor C into L plus L bar. So I have a decomposition into two Lie algebras. This is the Lie algebra condition for both L and L bar, which are transversal. But these Lie algebras sit inside the B plus of the complexification of B plus. They do not expand the full G. And furthermore, I have this other condition here. So in a basis for the L's and the L bar says that these are mutually dual, I have that this particular vector, which is an important vector in this story, is J times epsilon. So here J is just the natural complex structure on B plus tensor C given by this decomposition. So J acts as multiplication by I here and minus I there.
So kind of complementary.
Yeah. Yeah. In which direction I'm going? Here. Yeah. So this is the first term I wanted to present. So I have assumed that you have a generalized metric. So this decomposition with even dimensions. Assume that you have this. Assume that you have a decomposition of B plus tensor C as L plus L bar, such that L and L bar are Lie algebras, and this specific element, the sum of the AI and super I bracket, is in L plus L bar. And assume further that the rotation of this element is in the annihilator with respect to the pairing of the derived Lie algebra of L and the derived Lie algebra of L bar. Then there is an embedding of the n equals to 2 with these generators in the Lie algebra of on the vertex algebra of supercurrents. This has central charge 3 times n, and this is a specific formula for the generators.
So that's the quantization. It's embedding.
V cur G is the quantization of the Lie conformal algebra of currents. So this is a vertex algebra, and this is the n equals to 2 vertex algebra embedded inside here. And then telling you that the way you embed is via this formula. Okay. So our result generalizes a construction by Gessler for Manning triples, where what you need to do to recover Gessler construction is to set B plus orthogonal equals to 0. So this is the case where the quadratic Lie algebra splits as L plus L bar. Okay. And our geometric interpretation of these Killing spinor equations, even though they are not present yet here, tell us that a way of fulfilling this constraint here, which was also present in the work of Gessler, is to have that this W is holomorphic. It's like a holomorphic vector field on your background. And now the main theorem is this other result, also with Luis Álvarez Consul and Andoni de Riva de la Era, which is how to construct this n equals to 2 from solution of the Killing spinor equations. So if you start with a solution of the Killing spinor equations on a quadratic Lie algebra, says that the dimension of V plus is even and epsilon is holomorphic, meaning that epsilon preserves L, then it induces an embedding of the n equals to 2, which has this specific central charge, and this is the formula for the two generators. Okay. Our construction generalizes a construction by Maxime Sabstin and Raimundo Geloni, where they constructed pairs of commuting copies of n equals to 2 inside the Carroll-Derran complex, even though I'm not mentioning here the Carroll-Derran. And this is for generalized scalable geometric manifolds. But as I mentioned, these scalable geometric manifolds do not exist on Keller compact manifolds. So all the possible examples are Keller. And their proof also does not apply to this 0,2 supersymmetry situation that we are considering. Okay. Okay, and in the last -2 minutes, can I have 1 minute? Sorry. I would like to tell you about this 0-2 mirror symmetry on Hopf surface. Let me try to be brief. So if you have a smooth manifold and you have a closed freeform, then there is a canonical sheaf of vertex algebras. This is the one constructed by Malikov, Sherman, and Weintraub, which follows this general principle of quantization. So what you have is that you construct a current algebroid with this pairing and this bracket. You take this Lie conformal algebra, which is smooth functions on the manifold plus the sections of the current algebroid change parity, and then you define this lambda bracket. So quantization of this gives you this sheaf. And then the proposition is that if you have an even dimensional compact Lie group like this one, which is in the Hopf surface, then any left invariant solution of this twisted Calabi-Yau gives you a solution of the Killing-Spinner equations on this quadratic Lie algebra, and then provided by the dual of the Lie form is holomorphic, there exists an embedding of the n equals to 2 into the global sections of this chiral of the RAM. This is an example, which is the same examples I told you before. It's just the metric is the flat metric divided by norm of Z square in situ minus the origin, and then this holomorphic volume form is essentially the holomorphic volume form in situ quotiented by the norm of Z square. And this is the third. So take K equals to SU2 cross U1. So topologically, this is S3 cross S1. Fix H to be the Cartan freeform in the SU2 factor multiplied by some parameter L. Then for any real number, the solution of the Killing-Spinner equation of this twisted Calabi-Yau equation, which I presented in the previous slide, depending on the parameter X, is 0 to mirror to this other solution here. So minus omega X hat means that I have changed the orientation on the manifold. Okay, so the complex structure is conjugate to the usual one. And then the parameters satisfy this funny relationship. So X hat, which is the complex parameter for the 0 to mirror, is 1 over Lx. So if you remember from a previous slide, this Lx was this Apli parameter. It's like the replacement of the Keller parameter. So we realize this via this 0 to mirror symmetry, an exchange between the complex moduli and the Keller moduli in this non-Keller context using this Apli combination. And to be more precise, the way you realize the mirror involution for these n equals to 2 structures is via the construction of some automorphism on the U1 invariant part of the vertex algebra, of the sheaf of vertex algebras associated to this current algebroid. And the way we do it is using T-duality. Okay, so the manifold is SU2 cross a circle, and what you do to construct this automorphism is T-dualize this U1 direction. Okay, and this is how do you realize the mirror involution. Okay, so I stop here. Thank you for your attention.
Have these like a mirror for the half-twisted models. Do you have something analogous for like curved beta gamma systems?